Okay, in the last chapter you saw the 3 Newton's laws of motion. Uh, um, and today we'll do applications of those laws. Okay. We'll quickly review the 3 laws first. We'll remind you of the 3 laws, and then we'll look at applications. Okay. So let me start off with Newton's second law first. Newton's second law says, so if you have an object and there are several forces acting on this object. So for instance, there's the force of gravity. Here's the normal force. Here's an applied force, so you're pulling on this sled. And there's the friction force. Okay. The net force is the vector sum of all those forces. And the effect of this net force is it accelerates the object. Okay. So that's Newton's second law. Newton's second law says the acceleration is proportional to the net force acting on the object. So acceleration is and the proportionality constant is 1 inverse of the mass. Greater the mass for a given force, the smaller the acceleration. Okay, so this is Newton's second law. Newton's first law is just a special case of this. If the net force is 0, if the force is 0, then the acceleration is 0, and that implies velocity is constant. Okay, so Newton's first law is a special case of the Newton's second law. Okay, now of course you saw that this is the vector equation. When 2 vectors are equal to each other, that means their components are equal to each other. Okay, so that really is, in 3 dimensions, that's really 3 equations. Fx is equal to m times ax. Okay, the y component of the force is equal to mass times y component of the acceleration, and z component of the forces of the net force is equal to mass times z component of the acceleration. Okay, so there's Newton's second law. There's Newton's first law. Okay, and Newton's third law says when 2 objects interact, they apply equal and opposite forces on each other. So if she's pushing on the wall with that force, the wall pushes back on her with an equal and opposite force. Okay? So in nature, essentially all forces come in pairs. Okay? And you saw that. So here's another example of that. Okay, so Earth pulls me down with a force of 160 pounds, and I pull Earth back with an equal and opposite force. Okay? And so on. So every interaction, for every action, every interaction there are 2 forces involved. Action and a reaction. You know? All right, so we are going to apply these 3 Newton's laws to various situations, and that's what the rest of the chapter is about. All right, so here's a situation, and we'll learn what this expression free body diagram is. Okay, so here's an object. All right, now before I explain this diagram, I want to make sure that we understand the following simplification. Okay. So for instance, so let's say here's an object. This is an extended object, a large object, a real world object. Okay. Now let's say I apply a force like this, 10 pounds or 10 newtons, we'll keep it like that. All right. Okay. Actually, let me start off with the okay, here is the center of mass of the object. Okay, will this object move? Those are the only 2 forces acting on the object. Okay, this object will not move. Okay, it'll be at rest. Okay. How about now? Same two forces. Will this object move? No. Okay, now it'll spin. Okay, so the difference is the following. Okay, so for now, what we'll consider now till chapter 10, what we'll consider is forces that are applied that either go through the center of mass. If all the forces acting are going through the center of mass, the object won't spin. Okay. When the forces are not going through the center of mass, we'll learn about this in chapter 10. Their torques are zero. The sum of the torques are zero. Okay. So a simple way to remember this is if the forces acting do not have a rotational effect, then the sum of the torques is zero. Okay. So that's the kind of forces we'll consider. Here the torques are not zero. Okay. When this is true, what we can do is we can treat the object as a point object. And that's what we're interested in right now. Okay. So right now, in these kinds of situations, effectively you can think of all the forces are going through the center of mass. Okay. All we're concerned about is if you're applying forces to a car, the forces are such that we can represent the car as a point object effectively. Okay. That's what we're interested in. All right, so now let me make some room here. All right, here's what we're interested in. Okay, so this is the kind of stuff we'll be interested in. Okay, here's an object. There are several forces acting on this object. The three forces acting on this object are the tension in this rope there, the tension in this rope there, and the force of gravity on this object. Okay. Now let's say you're driving on the road. What is it that you want? You don't want this thing to move. You don't want this thing falling down. Okay. So what you want is the acceleration of this object to be zero. So what you want is the sum of all the forces acting on this object to be zero. Okay. So that's the kind of situations we want to analyze. Okay. All right. So again, like I said, while these two forces are not going through the center of mass, they have zero torque on the object. So again, we'll treat this as a point object. Okay. So there's the object. There's the object. Okay. The three forces acting on the object are this tension, and the weight, the force of gravity. And again, this object is at rest, acceleration is zero, so the sum of these three forces should be zero. And then you solve for these problems. Okay. So what is it that T1 plus T2, Mr. Newton tells us that the sum of these three forces should be zero. How many equations is that? I'm sorry? How many equations is that? This happens to be in 2 dimensions, so it's 2 equations. Yeah, very good. Okay, so you have this equation. It's really 2 equations. Okay, so T1x plus T2x plus Wx should be 0. T1y plus T2y plus Wy should be 0. Okay, so you have 2 equations and you can solve for 2 unknowns. Okay, so that's what the problem will be about. Okay, there'll be 2 unknowns and you're solving for that. Everybody understand that? Okay, so right now we'll keep things simple. All the forces acting on the object we'll be considering, it'll either have linear acceleration or it'll be at rest. Okay, so this is called a static equilibrium problem. Okay, so effectively all the forces are going through the center of mass. Okay, so here's another problem. Okay, there's the center of mass of the object. This tugboat is applying a force that goes through the center of mass. this tugboat is also applying a force that goes through the center of mass. So for instance, if you put this tugboat over here, that problem becomes tougher, because then that tugboat will make it spin, okay, and we don't want to do that right now, okay? So we want to keep it simple, okay? So right now, this force is going through the center mass, this force is going through the center mass, and the net effect of these two guys is it moves this barge in that direction. It makes it accelerate in that direction. And of course, that's on water, so there's a drag force, there's a resistance, so there's the drag force. Okay? And drag forces, friction forces are always in the opposite direction of the motion. Okay? So for instance, if the boat was being pushed in this direction, the friction force would be in that direction. All right, since this fella is not spinning, we're treating him like a point object. Okay? That's where the center of mass of the object is. And here are the three forces acting on this. And Mr. Newton has told us 300 years ago, okay, if the guy has non-zero acceleration, then the mass times the acceleration of the object should equal the sum of the three forces. Okay? And that's what we'll solve for. How many equations are that? How many equations is that? Again, this is a two-dimensional problem, so fx equal to max, fy equal to may. Okay? Again, you have two equations and you solve for whatever two unknowns they ask you to solve for. Okay? Again, this entire chapter is about applying f equal to ma for various situations. Okay? When the object is at rest, this is called a static equilibrium problem, okay? And if the object was moving at constant velocity, a was still zero, that would be a dynamic equilibrium, but most of the time we'll consider static equilibrium, okay? In fact, you will learn, so right now, if an object is at rest, that means the sum of the forces acting on it are zero. Okay? And if the sum of these torques, again, this you learned this is zero as well. Okay, this won't have linear motion, no linear motion, linear acceleration. And no angular acceleration. Okay, so for extended objects to be in equilibrium, in static equilibrium, for a bridge to be in static equilibrium, these two equations need to be true. And you will have a course later on called statics, which is entirely based on these two equations. Okay? So you'll all be doing, as engineers, you'll all be doing a statics class based entirely on this equation, these two equations. All right, so here's a situation where the net force is not zero, and so the acceleration should equal that. So the sum of these three forces, okay, the sum of this force and that force is this force, and plus the drag force, there's the net force in this equation. All right, so in this problem, this is a compound object. There are several objects. So here is a compound object as well, okay? And the thing is, Newton's laws applies to every object. Okay, so if you want to look at this motion, the object of this motion, the motion of this object, there are three forces acting on this guy. The weight, Newton, gravitational force, the normal force, okay, M1G, and the tension in there. So those are the three forces acting on the object. Okay, and so you can apply Newton's second law to this object. and you can apply Newton's second law independently to this object. Okay, so you apply it to all objects independently. Okay. So for object 2, M2G minus tension equal to M2A2. Okay. And since this guy is not moving in that direction, you know that this force is canceling that force. And tension is the only one making him accelerate, so tension is M1A1. And since the magnitudes of A1 and A2 are the same, we'll call it A. Tension is M1A, okay? That's the magnitude. M2G minus tension is M2A, okay? So there are the two equations for two objects. So if your system has 10 objects, you'll get 10 equations for the 10 objects. Okay. All right. So going back to this guy. Okay. So here's an object. Here's a composite object. There's the elevator and the person. And if you want the scale, you can look at the motion of any of the objects. Okay. You want to write the equation for this guy, look at all the forces acting on him. You want to write the equation of motion for this guy, you write down all the forces acting on him. You want to look at the equation of motion of this guy, just the scale, you look at all the forces acting on that guy. Okay. So for instance, let's start off simple. We want to look at the motion of this fellow. There are only two forces acting on him. The force of gravity, and he is in contact with the scale, and the scale is pushing him up. So those are the only two forces acting on him. Okay. Let's look at this guy, the elevator. This is the weight of the elevator. Okay. What is happening is gravity is pulling him down, and so he pushes down on the elevator, and that's the force the person exerts on the elevator. Okay. Gravity is pulling down on the scale, and the scale pushes on the elevator. That's the force. And there's tension in the cable. So on the elevator, what are the four forces acting? The weight of the elevator, the person pushing, and if the person was not there, it would just be the weight of the elevator and that. Okay. So with the person present, there are four forces. 1, 2, 3, 4. Okay. And so on the elevator, there's tension minus F. Okay, so if you take that as the positive direction, FP minus WS minus weight of the elevator should be equal to mass, the total mass times the acceleration of the elevator. Okay. So again, the message is when you have multiple objects, so this is easier to look at. The message is the following. When you have multiple objects in your system, you can apply Newton's laws to each object. Okay. Here's another system with multiple objects, two objects, and again you would apply Newton's law to each object. Okay. This was a device that Mr. Atwood came up with to measure the acceleration due to gravity back in the days, okay, a long time ago. So what he wanted to do was measure the acceleration of this object. Okay. Except that in the old days he didn't have a good enough timing device. This was falling too fast. So to slow the fall of this guy down, he invented this guy. Okay. And we'll actually do a lab with this thing, if the lab ever comes online. All right, so again, let's write down the equations for this. Okay. So for now, we'll assume that m2 is greater than m1. Okay? And let's say this guy is accelerating downwards like that. And so this guy will be accelerating a1, the acceleration will be upward, except that the magnitude is the same, so we'll use the same letter. Okay? And so for this guy, let's say the axis is pointing this way. What are the two forces acting on him? M2g and tension. So m2g minus tension is equal to mass times the acceleration. Okay? For this guy, again, when you're writing the equation for an independent object, for a given object, you can choose the axis independently of that. This problem is independent of this problem. Okay, so there is some relationship. I mean, the magnitudes of the acceleration are related. So for this guy, let's choose that as the axis, positive direction. Tension minus m1g. All right, so for this guy, that was the positive axis, and so this was this force had a negative y component or a negative component along that axis. Okay, tension minus that. Okay, so these are all magnitudes, and you can add these two equations. So m2 minus m1g equal to m1 plus m2a. So you see the magnitude of the acceleration of this guy is given by that expression. Okay. This factor, see, if m2 is equal to m1, if m2 is equal to m1, that would be 0. The acceleration would be 0. Okay. So this would not have any acceleration. If it was at rest, it will remain at rest, or if you get it moving, it will move at constant velocity. If m1 were 0, if m1 were 0, a would be m2 divided by m2, that would be 1, a would be equal to g. So here is a device where you can dial the acceleration to any value you want between 0 and g. Okay? And that's what Mr. Atwood invented. Okay? So if you make the acceleration as small as possible, now it'll take a much longer time to fall down. You can measure that acceleration. You can measure this guy and calculate g. And that was the idea. Okay? All right, again, the message we are trying to convey is when you have a system with multiple objects, you can apply Newton's laws to individual objects. Okay? All right, now we'll consider friction forces. Okay. So let me. So there are two kinds of friction forces. We'll consider static friction forces and kinetic friction forces. Yep. And friction forces, they're called friction forces when two solid surfaces are in contact with each other. When a solid object moves through a fluid, that's called a drag force. Okay, that's just terminology. That's also a friction force, but it's called drag force when a solid object moves through a fluid. Okay, so for instance, when you drive your car, half your money is plowing through air. The air drag is half your money. Okay? All right. So let's Okay, so here is a solid object sitting on this solid surface, and if it wants to move, it encounters friction forces. So between these two surfaces, the friction forces arise because of attractive forces between the molecules of the box and the ground. Okay, so we have friction. Okay, so what we'll do is the following. Okay, let's say. So you can see that I've applied a 90 Newton force. I'm pushing with a force of 90 Newton, and the object didn't move. And the reason was because there's a static friction force between that object and that object. Okay, the molecules of the ground are attracting the molecules of the box and pulling it back. So that's a static friction force. How much is the static friction force now? 0. Okay. All right. How much is the static friction force now? 30 newtons. Okay. So you can see that the static friction force can change. So friction forces are denoted by a little f. The subscript s telling you that it's a static friction force. Okay. And it can be anywhere from 0 to obviously a maximum value, because you can apply a force large enough to get it moving. Okay? And in a second, we'll find out what the maximum static friction force is. Okay, so let's go back to our app and find out what the maximum static friction force is. All right. Okay, so 96 newtons. All right, so 119 newtons. That's not quite moving it. Okay, so the maximum static friction force is greater than that. Okay. So the maximum static friction force in this case was 125 newtons. Okay. Okay, so let me ask you this. Now let's do the same experiment, except that I'll put a little glue on the bottom of the box. What will happen to the static friction force, the maximum static friction force? It'll go up. Okay, so you obviously know that. Okay, it turns out that all right, so here's the weight of the box, and if nobody's pushing down, here's the normal force. The normal force, in this case, the normal force is equal to the weight, and it turns out that Fs max is equal to mu s times the normal force. This fella is called the coefficient of static friction. All right, so when I put glue on the bottom of the box, what did I do? I didn't increase the weight of this guy, so the normal force didn't change, but the maximum static friction increased. What? You change the coefficient. So mu s measures the stickiness of the two surfaces. Okay? What are the dimensions of this mu s? What are the units for mu s? Okay, this is a force. That is a force. So this is dimensionless. That's just a number. Okay. What are the values this number can take? Zero would be a frictionless surface. And?
Negative would be like reduced friction, correct? Or
No,
you can't go negative.
it can't go negative. So frictionless is the best you can do. And the worst you can do is infinity. That's super glue. Okay. So this is a dimensionless quantity, and it can go from 0 to infinity. Okay. All right, let's go back to our app. Okay, so we saw that in this case, the maximum static friction force was 125 newtons. Okay. Now, if I increase friction, what would I be doing? I would be increasing mu. Okay. You'll see there's a mu s and a mu k. If I increase friction, okay, so let me do that a little, and you see it didn't move, and all right, so you see that I've increased the mu. Okay, let me go back to okay, there's the maximum static friction force. So now if I apply a force greater than that force, the object will start moving. Once the object starts moving, there's a friction force, but that becomes a kinetic friction force, okay, once the object is moving. And that kinetic friction force always is smaller than the maximum static friction force. Okay? All right, so once the object starts moving or accelerating, moving, it'll start accelerating if you maintain that force. So once the force is greater than the maximum static friction force, the object will move, and the static friction force will turn into a kinetic friction force, and this guy, the kinetic friction force, is always smaller than the maximum static friction force. Okay. Because once you break loose, the bonds, you're making temporary bonds, and they're not holding on as strongly, essentially. Okay. All right. So, well, let me go back. Okay. So now I'll increase the force. So the applied force is 175 newtons. And this force, now the friction force is a kinetic friction force, and the object will accelerate. Okay?
I have a question.
Mm-hmm.
So will be this new force minus the max original static friction force?
Yeah, the new force is that applied, the net force is that applied force minus the friction force. Okay? Okay, so again, friction arises because of the jagged nature of the surface, and it's these temporary bonds that are forming, that are causing the friction force. So if the object wants to move in this direction, those bonds are pulling the object back in the opposite direction. If the object wants to move in this direction, those temporary bonds are pulling in this direction. Okay? So part of the friction is because of the roughness of the surfaces in contact. However, much of the friction is due to the attractive forces between molecules of the two objects. Okay? In fact, perfectly smooth surfaces of similar material would adhere. So that's what a crystal is. You know, a perfectly smooth surface, you can't, they'd have a very large friction. Okay. So two surfaces in contact the actual microscopic area of contact is only of the order of 1 part in 10,000. So the actual area of contact is very small. Okay. All right, so here is the maximum static friction force. You saw that this is the applied force. You apply a force like this, and the static friction force will be equal to that. So this slope of this line is 1. You apply this force, that's the static friction force. At this force, the object breaks loose, and that's the maximum static friction force. So if you apply a force greater than that, the object will break loose, and once the object breaks loose, that's the kinetic friction force. No matter how, once the object moves, the kinetic friction force remains constant, is constant. Okay. So there is the maximum static friction force is the coefficient of static friction times the normal force. The kinetic friction force is mu k times the normal force. Okay, so since this guy is smaller than that, mu k is less than mu s. Yeah. All right, here's a table for various kinds of surfaces in contact. Here's rubber against dry concrete, rubber against wet concrete, rubber against dry concrete. Mu s is 1, mu k is 0.8. Okay. Let me show you what these numbers mean, and then we'll talk about a application. Okay, so for rubber on concrete, okay, why would be interested in this? Your car tires are rubber, roads are concrete. Okay, that's one application. Mu s is equal to 1, mu k is equal to 0.8. Okay. So here's a rubber block sitting on concrete. Let's say this thing weighs 100 newtons. Okay. And so the normal force is 100 newtons. Okay. So the maximum static friction force is mu s times Fn equal to 1 times 100 newtons. Okay. So what this is telling you is to get this block moving, you have to apply a 100 Newton block sitting on concrete. You have to apply 100 Newton force to get it moving. The kinetic friction force is mu k times the normal force, 0.8 times that, 18 newtons. And to keep this moving at constant velocity, all you need to do is balance the kinetic friction force. So to keep it moving, all you need is 80 newtons force. That's what that means. Okay. All right, so that's what those numbers mean. So think of 100 Newton block sitting and 100 Newton block sitting on this surface. So a steel on steel surface, you need 100 Newton block of steel sitting on a steel surface. You would need 70 newtons to get it moving and 60 newtons to keep it moving. Okay. Wood on wood, 50 newtons to get it moving and 30 newtons to keep it moving. Okay. Yep.
How come on the bottom, curling stone on ice doesn't have a US?
Well, so ice.
Creates a barrier.
No, if you can't make the same consistent, if it's not repeatable, they don't put that there.
So it's just so small that you can't even really measure it properly.
No, the ice is not
It's not consistent.
consistent. It's not the same every time. Okay. And if the, yep, so this table doesn't have it. Okay, so these are numbers for various surfaces. Your joints, how long do they have to last? Your entire life. So those have some of the lowest kinetic coefficient of frictions. Okay. The more friction you would have, more likely you're to cause cellular damage. Okay. And all right, so look that up. All right, now here's another application that you need to be aware of. See, these numbers are not. Somebody's gone to trouble to measure these numbers, and here's the reason why. So, for instance, okay, so again, we'll sort of. All right, so let's say you're going at 100 miles an hour and you want to stop. Okay. The greater the acceleration, the smaller the stopping distance. Okay, so this is a safety issue. All right, now so we'll do this in 2 steps. So now first we'll try and accelerate, you guys. Okay. So when you accelerate, what your engine is trying to do is spin the car faster and faster. Okay. But if your tire slips, if you're doing it on, let's say you try and accelerate on the beach, you can't accelerate because the tire is slipping. Okay. So this guy, if you want to accelerate, you don't want your tire slipping, so this guy is not moving, so there is a static friction force in this direction, preventing it from slipping. And that is what accelerates it. Okay? So the tire wants to slip, the static friction force is preventing it, and that's what makes you accelerate. All right? Now let's do the next thing. Again, you'll have to think about this when you first hear about this. It's kind of mind-blowing. But all right, now you were going at 100 miles an hour. You are trying to stop, so you want a large acceleration in this direction. Okay. You apply brakes. Okay. The brakes, what are they trying to do? The wheel is spinning. They're slowing down the spin. Okay. So now, if this thing doesn't slip, then the static friction force is in this direction. And that's what's slowing you down. If the brakes lock, the tire is not spinning anymore. Now you're sliding. That would be a kinetic friction force. Okay? So here is rubber and concrete. If your brakes do not lock, the static friction force is stopping you. That acceleration is 20% greater than that. If the static friction force is stopping you, this acceleration is 20% greater than that. Stopping distance is 20% smaller. Okay? So that's why anti-locking braking system. Now, you guys are all born with anti-locking braking systems, but if you have a car which doesn't have anti-locking braking system, you're paying higher on insurance because your stopping distance is 20% greater. Yep. All right, so, and again, your stopping distance decreases when it's on a wet road. Okay. And it decreases tremendously on icy roads. Okay. All right, now we'll be interested in objects like this, skiing downhill skiing. All right, again, as long as this guy has only linear motion, he's not spinning, you can treat him as a point object. That means there are no torques acting on him. Okay. Let's look at all the forces acting on him. Here's the force of gravity. Here's the normal force, and here's the friction force. So there are only really three forces acting on him. So we will represent him as a point object. Here's the force of gravity, mg. Here's the normal force. And there's the friction force. Okay. Again, right now we're ignoring drag forces because they're harder to deal with. Okay. All right. So in this business, okay, this guy is annoying. Okay. He's not useful. Well, at least in this form. So what you do is you want to break this into that component and that component. Those are the useful components of the weight. And this guy is mg. We saw this last time, mg cosine theta and mg sine theta. Remember, the superposition principle told us that you could replace that force by those two forces. Okay. So now all the forces are in convenient form. Okay. So what is happening if this guy is not coming off the slope, then that means this force is balancing this component. And if he's accelerating downwards, that means this force is greater than that force, than the friction force. And if he's coming down at constant velocity, that means this force is equal to that force, and so on. Okay. And of course, if this force is greater than this force, then he's not moving and he's not having any fun. Okay. So that's the deal. All right, so here's an interesting problem and a serious problem. Again, you got to remember that you apply Newton's laws to every object. Whatever object, if you want to look at the motion of object A, then you apply Newton's laws to object A. You want to look at the motion of object B, then you apply Newton's laws to object B. Okay, so here's a truck that is accelerating. Okay, so if you look at the whole object, Newton says there's no two ways around it. This whole object is accelerating, so the net force on that whole object should be the mass of the whole object times the acceleration. So that's the acceleration, that's the force, that's the equation for the entire object. How about this guy? What is the acceleration of this guy? What is the acceleration of this guy? I'm sorry? It's the same. Okay. So Mr. Newton says the force on the crate should be mass of the crate times the air. The crate doesn't have an engine. Where is the force coming from? Where is the force on the crate coming from? I'm sorry?
The friction keeping it attached to the drive.
Very good. It's the static friction force. Okay, that's accelerating the crate. All right. So you put an ice block on an icy truck bed and you accelerate away. What are you going to do? Your ice block will stay back. Okay? Now that doesn't happen too often. That's not a problem. Here's a very serious problem. All right. So here's a truck that's going at 100, well, okay, will be 80 miles per hour. This is a real problem. So let's say a wall jumps up in front of the truck. The truck stopped. It had a great acceleration in this direction. Okay, now this guy, you want this guy to stop as well. If the static friction force is not capable of stopping him, this guy will come flying. Okay, so for this driver, it's a double whammy, the wall and his heavy load. Okay. And people have lost lives on that. Okay. So that's why you'll see those heavy loads chained down. Okay. They don't want to rely just on static friction force. That's what that is. No truck will accelerate fast enough for this to fly off, so you don't have to worry about that. You just have to worry about walls jumping up in front of you. Yeah.
So when you have the straps on, it's no longer relying on the friction, it's
This-
relying on tension.
Yeah, it's helping friction, yep. Yeah. Well, actually, the friction is helping it, so yeah, that force is large enough to hold it back. And the heavier the object, straps change into chains. All right. So let's say you're driving. Now there are a lot of roundabouts on roads. So let's say you're going around a roundabout at constant speed. Are you accelerating? And why are you accelerating?
Direction's changing.
And the directions is changing. So when only the direction of the velocity changes, the acceleration is perpendicular to the velocity. It's perpendicular to your trajectory. Okay? So when only the direction of the velocity changes, there is the trajectory, and the acceleration is perpendicular to the trajectory. Okay? And it's called centripetal acceleration. Mr. Newton says if you have an acceleration, you have to have a force. Okay? So now let's look at a side view of this thing. So here's the center of the road, here's the car. Okay? So you want a acceleration in force in that direction. Well, gravity cannot provide that force. The normal force cannot provide that force. So you need a force in that direction. Gravity is acting this way, normal force is acting that way. What is providing that centripetal force?
Friction.
What's that?
Friction.
What friction?
Static friction.
So it's the static friction between the car and this and the road. Okay. The car wants to go straight, meaning slide off. You're trying to bring it this way. So it's a static friction force in this direction that's providing that. All right, here's the problem. So how did the static friction force come about? Molecules in the tire are attracting the molecules on the road. Okay, and you leave behind a few molecules. Okay, so you keep going in circles, drive on a straight road at constant speed and drive in a circle at constant speed. You will wear out your tires much faster on the circle. Same speed, same constant speed. Okay, that's because you're leaving rubber molecules on the road. And this would really cost the nation billions of dollars. So if every curved road was flat, you'd be leaving so much rubber behind that it would cost billions of dollars. So how do you fix that? You bank the roads. Okay, so So that's what we're going to do. Okay, so we're going to bank the road. Okay. And let's see how it saves us money. Okay. Gravity never quits, so there's the weight of the car. And okay, so for a given angle and for a given weight, well, here's the normal force, and this normal force is constant. Okay, so what is happening is this is the angle of the road, that's equal to that, and so this component of the normal force is balancing the weight. So this is n cosine theta. N cosine theta is equal to mg, the weight. And this component, n sine theta, is providing you the centripetal force. Okay? So, and that will be just the right centripetal force for a given speed. So for a bank angle, there is a specific speed that you need to drive such that this is providing the centripetal force. Okay, if this guy is not enough, then you'll need a static friction force. And if this guy is too much, then you'll need a static friction force in that direction. Okay, so it turns out for only a specific speed will the static friction force have to be 0. Okay, and that specific speed is the following. So for that precise speed, n sine theta is providing you the centripetal force, which is that guy. N cosine theta is balancing your weight. And now if you divide that equation by that, tan theta is equal to v squared by gr. Okay. So for this bank angle, if you go at that speed, the normal force provides you the centripetal force. If you go faster than that, you have to have a force, static friction force helping you in that direction. If you go slower than that, you have to have a static friction force in that direction.
Is that why racing tracks?
I'm sorry?
Is that why racetracks tend to be at angles?
Yeah, they're going to be at an angle. I mean, but so our racetrack is at an angle of 30 degrees, and for 90 miles an hour, you don't need any static friction force. Of course, those guys are going crazy. They want to drive around at 200 miles an hour. So, but if it was a flat road, they couldn't go at 200 miles an hour. All right, there's something interesting about this guy. There's something interesting about this equation. Do you notice? No. So what is the bank angle for the car? That thing. What is the bank angle for a truck? Same thing. So if you, on the exit, those speeds are related to the bank angle of this exit. It doesn't matter whether it's a car or a semi-truck going through there. The normal force is providing the centripetal force. So the road can be as icy as it wants. If you're going at that speed limit mark, you won't slip off the exit. Okay? So it's independent of the mass. All right, and so again, the idea is if you're not using any static friction force, you're not leaving rubber on the road, and your tires will last longer. Okay? And since they obviously bank the roads, what does that mean? It costs the country less to bank the roads than in rubber. Okay, and it's a safety issue as well. A plane could not make a turn unless it banks. Okay? And when it banks, so the lift is always perpendicular to the of the wings. Okay, so this component of the lift is balancing the weight, L cosine theta. And this component, L sine theta, is providing the centripetal force. Okay. All right, I want to continue and finish this lecture because I'm recording it and I don't want to stop and start the recording. Yeah. So now we'll talk about drag forces. What are drag forces?
When a solid goes against
I'm sorry?
when a solid force goes against a fluid.
When a solid object is moving through a fluid, that's drag forces. Okay? Do you encounter this in your life? Well, I'm sorry? Swimming. Every time you drive your car, you're moving through air. That's where half your gas money goes. Okay? All right, so go drive on the moon and your gas mileage will double. Okay. All right, so the magnitude of the resistive force when a body moves in a fluid depends on speed in a complex way. So in general, it's hard to handle, and so we consider objects moving in air. For small objects falling slowly, such as dust particles falling in air, the resistive force is proportional to the speed. So when you have small objects falling, the drag force is proportional to speed. Yeah. For large objects, the drag force is proportional to the speed square. Yeah. C is the drag coefficient, and aerodynamically shaped objects, C is smaller. Okay. So C for a Tesla car is smaller than for a UPS truck. Okay. Rho is the density of the fluid through which you're moving. So when you're driving, rho is the density of air. A is the cross section, and the cross section is, so when this object is moving in this direction, that's the area of cross section. Okay. And V is the speed. So you can see that if you double your speed, the drag force increases by a factor of 4. Okay. So for large objects, it depends on that. Okay. So drag coefficients typically are 0.5 to 2, depending on the type of vehicle. Okay. So for instance, all right, we'll come to this in a second. All right, so drag forces are proportional to speed square. Okay, so let's talk about this. Okay, you jump off a plane, or you step off a plane. What is the force on you right now? What is the drag force on you right now? You just stepped off a plane and not on the ground, in the air. Hmm? So right now your velocity is 0, so it's the force on you is just the force of gravity. Okay, your acceleration is g. Okay. Now as you gain speed, the drag force is increasing. Your acceleration is less than g, but you still have a positive acceleration, so you keep speeding up. Eventually, the drag force gets to be equal to the force of gravity. Now the net force on you is 0, so your acceleration has gone to 0 and you have reached terminal velocity. Okay. So all objects will reach terminal velocity when falling down, okay, in air. Okay, so when you reach terminal velocity, the drag force is equal to your weight. Okay. Now, in this equation, larger A is smaller the terminal velocity. Okay, so in this configuration, A is smaller than in this configuration, and I believe in this configuration, if you fall head first, your terminal velocity is about 180 miles an hour or so. In this configuration, it's about 120 miles an hour. Okay. Nolan should know this because DeLand is the skydiving capital of the world. All right. Anyway, so larger A is smaller than terminal velocity. Okay, so the terminal velocity is 2 times the weight times the drag coefficient, density of the fluid in which you're falling, times the area of cross section. Okay, so here's a velocity profile. Okay, so this is time, and you can see that the slope of this line is your acceleration, and the acceleration is going to 0 when you reach terminal velocity. Okay. And drag is a good thing, I mean, in many situations. So for instance, a skydiver, this cross-sectional area 0.7, that is falling flat like this, and that's about 120 miles an hour. Okay, a little more than 100. If it rained baseballs, the terminal velocity of baseballs would be 100 miles an hour. Faster than, so those fast pitchers are throwing it almost at, okay, so I can throw a pitch as fast as the fast guy. I just have to drop it from the top of a mountain. Actually, from a plane. So if it rained down golf balls, they would rain down at 100 miles an hour. Hailstones about 40 miles an hour, and you can see what kind of damage they cause on cars and stuff. You can't walk in a hailstorm. Raindrops about 20 miles an hour. Okay. Here's an object. So here's an expression for. Okay. So the quadratic dependence on air drag upon velocity does not hold if the object is very small. So this is for small objects. It's going very slow or is in a denser medium than air. Okay, so if you throw a, so if you shoot a, okay, if you shoot a cannonball underwater, okay, then the drag force is proportional to velocities. Okay, is proportional just to the velocity is given by Stokes' law. Okay, so the drag force is eta is the viscosity of the fluid. So, viscosity for honey is greater than viscosity for water. Okay, so drag forces in honey would be greater than in water. Okay, R is the radius and so on. Okay, so this is the Stokes' law for small objects in denser medium than air. Okay. When are Newton's laws valid? So Newton's law says force is mass times acceleration. Okay, that is, if you're accelerating, that means that force is acting on you. Okay. And these guys are valid in inertial frames of reference. What is an inertial frame of reference? An inertial frame of reference is a frame of reference that is either at rest or moving at constant velocity. anything spinning, a frame of reference that is spinning is not an inertial frame because it's accelerating. The Earth is spinning on its axis, so it's a non-inertial frame of reference. But that non-inertial aspect you only notice if you're observing something that's happening over hours, okay, on that time scale. All right, so the Coriolis force is a fictitious force. It's not a force, not a true force, but it appears to be a force that you observe in a non-inertial frame of reference. Okay, so let's see what is happening here. Okay. So what this says is in the northern hemisphere, if you have a low pressure, cyclonic winds will be anti-clockwise. Around a high pressure, they'll be clockwise. Okay, and in the southern hemisphere, it's opposite. Okay, so let's see what is really happening here. All right, we'll do it. So here's the Earth. It's spinning about its axis, so there's the equator. The Earth takes 24 hours to go around once. Okay. The radius of the Earth is 4,000 miles. So at the equator, the circumference is 2 pi r. 2 pi is roughly 6. That's 4,000 miles, or 6 times 4, 24,000 miles. Okay, so a point on the equator is going at 100,000 miles per hour. What is the speed of the North Pole? How fast is the North? 0 miles an hour. Okay, so the speed is decreasing. So somewhere in New York, I don't know, is going at, let's say, 800 miles per hour. What is the air above the equator traveling at? Thousand miles an hour. What is the air above New York traveling at? 800 miles an hour. Okay? So now let's create a low pressure here. Again, I'm going to blow up this diagram. Okay? This air was going at 1,000 miles per hour. This air was going at 800 miles per hour. And now we'll create a low pressure. So this air will start moving in that direction. This air will start moving in this direction. Okay. Remember, this land was traveling at 900 miles per hour. Okay. So when this air is moving, this was traveling at 1,000 miles per hour. This land is only traveling at 900 miles per hour, so this air will get ahead. Okay? And this packet of air will fall behind. Okay. So air that should have been traveling at constant velocity, since there was no force acting on it, but it's being deflected. Okay, that was because you're observing it from a non-inertial frame of reference. Okay, so you have to invent this force. There must be some force that's deflecting it. It's not being deflected. The ground underneath it went faster. That's all. Okay, and that's the Coriolis force. Okay, so you get a counterclockwise wind around at low pressure in the northern hemisphere. Okay. All right, so that's what that is. So you guys have seen geese flying in formation. They'll be coming here soon. They probably started their migration already. Okay, why do they fly in formation like that? I'm sorry?
Reduces drag.
It reduces drag.
They also hit each other.
What's that?
They also hit each other.
No, it reduces drag. Okay, so for instance, okay, so let's say if a bird flies by itself from point A to B, and if it uses 1,000 joules of energy, and if it was flying like this and it still used 1,000 joules of energy, then it wouldn't fly in formation. So obviously, it must use less energy in flying in formation. So if it uses 800, I'm just making up numbers, 800 joules by flying in formation, you'll of course fly in formation. Okay, is everybody working equally hard here? Who's working the hardest? This guy is working the hardest. So what gives? Who would volunteer there? Huh? So they take turns. You fly there, and then you fly there 10 minutes, then you come, the next person goes, and so on. Okay. So you distribute the workload equally. Okay. In fact, you've seen this when bicyclists go drafting, and if you're drafting at the right distance and so on, you can reduce the drag forces by up to 50%. So if you do it right, instead of 1,000 joules, you can take 500 joules to go from point A to B. You're going to do it every time. Okay. So I like to say this in my classes. You guys are going to be engineers, and if you want the best solution to a problem, where do you go? You go to nature to look for it. Nature has had thousands of millions of tries, and it's had millions of years to perfect a solution. Okay? So nature has the best solution, and there is a field like that, biomimetics. You're mimicking nature. Okay?